Edward Condon was soon immersed in the world of physics and theoretical physics. At its core, physics is a branch of science that studies matter, momentum, force, energy, and the ways that they interact and behave through space and time. There are many subfields of physics like classical mechanics, which describes the behavior of solids, gases, and fluids. Thermodynamics, which deals with the properties of heat, work, and temperature. Electromagnetism, which deals with the properties of electricity. Optics, which studies the behavior and properties of light and the electro. And there was Edward Condon's major, theoretical physics. Theoretical physics is a subfield of physics that employs mathematical models and abstractions of physical objects and systems to rationalize, explain, and predict natural phenomena. During this time, the field of physics in America was in its infancy and underdeveloped when compared to Europe. According to Condon in the 1920s, most Americans didn't even know what physics was. Nevertheless, Berkeley would go on to develop one of the best physics programs in the country. And along with Edward Condon, Berkeley would come to foster physics minds like Ernest Lawrence, J. Robert Oppenheimer, and Philip Morrison. At Berkeley, Edward Condon received his undergraduate degree in theoretical physics in 1924, then PhD in physics in 1926. After completing his PhD also in theoretical physics, Condon would decide to further his education in the physics capital of the world. In 1926, Edward Condon arrived in Germany for a 2-year teaching fellowship where he studied at the University of Gutenberg. Condon would grow close with fellow American physicist J. Robert Oppenheimer, who was also in Germany to further his physics education. Condon and Oppenheimer enjoyed Germany and all the cutting-edge physics they were absorbing. At this time, Germany was one of the physics epicenters of the world, and physicists like Erwin Schrödinger, Werner Heisenberg, and Max Born were pioneering a new field of physics called quantum mechanics, a subfield of physics that describes the behavior of atoms and of the particles and forces that composed atoms. Quantum mechanics was created to account for the newly discovered quantum model of the atom. In order to better understand what quantum mechanics is, let's briefly review the history of man's understanding of the atom and the different atomic models that were developed over time. The word atom is derived from the ancient Greek word atomos, which means uncuttable. The earliest concepts of the nature of the atom were debated in ancient India and ancient Greece. The modern atomic model would begin to take shape nearly 2,000 years later. In 1803, John Dalton created the first modern atomic model, the solid sphere model. He theorized that different elements were composed of entirely different atoms, which had different properties. He also theorized atoms of different elements can form compounds. This early atomic model had no subatomic particles. Through various instrumentations, scientists were able to determine the atomic weight of different atoms, and this is what would form the basis of the periodic table. Different elements had different atomic weights and different properties. Some of the next major discoveries would occur around the turn of the 20th century. In the 1890s, it was discovered that while most naturally occurring atoms were stable, there were some that were deemed unstable, usually due to a high atomic weight or unbalanced components. Unstable atoms would spontaneously release energy and shed particles. This process would change their atomic structure without outside influence. This process of unstable atoms changing their atomic structure would be called radioactivity, and the residual energy released would be called radiation. And also during this time, it was discovered that atoms are composed of positive and negative charges. The electron was first identified in 1897. Electrons are subatomic particles with a negative charge. To account for the discovery of negative and positive charges within an atom, the atomic model was updated the plum pudding model in 1904. The plum pudding model theorized that atoms were composed of both positive and negative charges. In the plum pudding model, atoms contain negatively charged electrons that were thought to be scattered across a positively charged sea, like a plum pudding. In 1911, Ernest Rutherford discovered the proton, a subatomic particle that were larger than electrons contained a positive charge. To account for protons, the atomic model would be updated once again to the nuclear model. The nuclear model stated that positively charged components of an atom did not exist in a plum-pudding sea across the atom, but in the newly discovered protons, and these protons were contained in a small central component of the atom, called the nucleus. The negatively charged electrons were positioned in an orbit around the proton-filled nucleus, and the opposing positive and negative forces of the protons and electrons kept orbit in a fixed position. And the positive and negative charges repelled subatomic particles with the same charge, making it nearly impossible to use protons and electrons as tools to manipulate atoms because they would be repelled by these strong positive or negative forces. In 1913, Niels Bohr introduced the planetary model of the atom, which stated that the electrons orbiting a nucleus were doing so in orbits of fixed sizes and energy. And in the 1920s, when Edward Condon was beginning his physics career, the atomic model was once again updated to Schrödinger's quantum model. Like previous models, the quantum model theorized that the atoms consist solely of a central nucleus containing positively charged protons, and orbiting the nucleus are negatively charged electrons. Schrödinger's quantum model would differ from previous atomic models by theorizing subatomic particles move so erratically it was impossible to know their exact locations at a given time, and that the electrons orbiting the nucleus at different energy levels were doing so in a cloud of probability. Since the nature of subatomic particles in the Schrödinger model are rooted in approximations that could not be represented by classical physics and mechanics, quantum mechanics was developing to account for this nature that relied on probability and approximations. Quantum mechanics utilizes probability to measure approximations of a given particle's energy, momentum, and other physical properties. And quantum mechanics would employ wave mechanics as well as matrix mechanics, which used algebraic matrices to represent the different states of subatomic particles. Edward Condon and Robert Oppenheimer enjoyed their time in Germany. They were on the cutting edge of physics, studying under European scientists pioneering quantum mechanics. Both Oppenheimer and Condon were quick learners and highly proficient in quantum mechanics and quantum theory. And before long, it was time to return to America. Using the knowledge he obtained in Germany, Edward Condon began touring U.S. universities, helping bring German knowledge of quantum mechanics to the United States. In 1929, in cooperation with Philip M. Morse, Edward Condon wrote Quantum Mechanics, the first English-language text on the subject, and Condon was credited with discovering Condon-Shortley phase Frank Condon principle and Slater-Condon all principles of quantum mechanics that are used today. Before long, Edward Condon was a nationally recognized leader in atomic physics and quantum mechanics. Edward Condon joined the American Physical Society, American Society of Photogrammetry, the National Academy of Sciences, and American Association for the Advancement of Science. Edward Condon became a professor at Princeton, which had one of the leading physics programs at Princeton. He would become acquainted with fellow physics professor H.P. Robertson, who would later run the CIA's Robertson panel in 1932. While Condon was still at Princeton, another revolutionary discovery would be made to the structure of the atom, the discovery of the neutron. The neutron is a subatomic particle that contains no charge and is positioned in the nucleus, along with positively charged protons. The negatively charged electrons are still orbiting the nucleus on probability clouds. Since the neutron has neither a positive or a negative charge, it would not be repelled by the strong forces that affected protons and electrons. And because neutrons were not repelled by the other components of atoms, neutrons could be used as a tool in ways that other subatomic particles could not be.
This billiard ball is a proton. No stream of light particles like electrons, no known type of wave, could have any more effect on such a body than these rice grains have on the billiard ball. But another particle of equal mass would share its energy on collision, just as this second ball imparts half its energy to the first as it pushes it away. A particle of unit mass, but without electric charge, and so very difficult to detect.
Scientists soon began taking the newly discovered neutron and bombarding different elements of the periodic table. Often these experiments would result in the creation of separate isotopes for a given element, or combining and transforming elements into completely different substances. The process of nuclear fusion would be discovered during this time, the combination of two lighter atoms or particles into larger ones, and this process would create new substances and release energy. The discovery of the neutron and nuclear fusion raised the relative significance of atomic physics and quantum mechanics. And like many physicists following the discovery of the neutron, Condon's interest would turn towards nuclear physics. Edward Condon focused on applications of new methods of quantum mechanics to problems of atomic and molecular structure and the interpretation of radioactivity. By this point, theoretical and quantum physics had gone from obscure sciences most Americans had not heard of to a well-known science with broad practical applications. In the 1930s, physicists were responsible for introducing the world to radar, FM and AM radio, the first Xerox copying machines, new kinds of long-lasting batteries, and many other things. And physicists were in hot demand. Edward Condon would leave academia in 1937 to work at Westinghouse Electric and Manufacturing Company, and while there he would invent a device called the Nimitron. The Nimitron was a machine that recreated the ancient math game called NIM. This device was revealed at the 1939 New York World's Fair, and the Nimitron machine is credited with being one of the first machine games and first examples of machines' ability to represent data. Although the Nimitron was popular at the World's Fair, it was too expensive to mass produce and sell, and with World War II looming on the horizon, Condon focused on research and development of microwave radar and nuclear physics.
Japan has brought 55,000 more troops up the Yangtze River. And as the Chinese armies mass in a great arc round the city's western outskirts, it's war within a few...
Germany has invaded Poland and has bombed many towns. General mobilization has been ordered in Britain and France.
When World War II broke out across the globe, many of the America's prominent scientists would go into research and defense. Edward Condon would help organize President Roosevelt's National Defense Research Committee, a scientific research and development effort led by Vannevar Bush. Edward Condon also helped MIT organize their infamous Rad Lab, which would feature scientists like Carl Compton, Ernest Lawrence, and John Trump. In Europe, atomic physicists made another very important scientific discovery. When neutrons were bombarded against certain isotopes of the unstable elements, uranium or plutonium, something interesting would occur. It was discovered that if certain unstable isotopes of uranium or plutonium were bombarded with neutrons, it would result in breaking of the atom into multiple smaller and more stable elements. It was also discovered that the atomic splitting process would have a side effect of releasing a large amount of energy in the form of gamma radiation, and importantly, would release stray neutrons. This process would come to be known as nuclear fission. To compare nuclear fusion and nuclear fission, as it was understood at the time, nuclear fusion occurs when bombarding an element with neutrons results in the combination of two lighter atoms or particles into larger ones. Nuclear fission occurs when bombarding certain unstable elements like uranium or plutonium with neutrons results in the splitting of atoms into two smaller atoms, and this process would release noticeable amounts of energy and stray neutrons. Furthermore, it was theorized that if you were able to get large enough quantities of uranium or plutonium and attempted nuclear fission, the neutrons and energy that were released in the initial splitting of the atoms would go on to bombard nearby atoms, causing the splitting of these nearby atoms, releasing more energy and more neutrons, and this process would repeat and repeat, causing a chain reaction. And this chain reaction would release a huge amount of energy, and it was theorized it could create an explosion bigger than any chemical reaction. One saving grace regarding this theorized superbomb was that the specific isotopes of uranium and plutonium needed for the desired fission process were very rare and extremely expensive to produce quantities that would lead to desired result. Following Japan's attack on Pearl Harbor, America officially joined World War II, and all aspects of American society honed in and focused on winning the war. Amidst this climate, Edward Condon began hearing rumors amongst his scientific colleagues that a top-secret project was being organized to build off of the discovery of nuclear fission and split the atoms of uranium and plutonium to harness the power of the energy released in the chain nuclear reaction and create the theorized superbomb. And soon these rumors would come knocking at Condon's door. J. Robert Oppenheimer, Condon's fellow Berkeley alumni who studied with Condon in Germany, showed up and asked Condon if he would join him in a top-secret project that would come to be known as the Manhattan Project, the massive scientific project to create the first atomic bomb. The Manhattan Project composed of some 130,000 workers, various project sites around the country, and a budget of billions of dollars. And J. Robert Oppenheimer had been tasked with helping organize this effort. J. Robert Oppenheimer recruited Condon to be the associate director of Los Alamos, one of many sites around the country which were taking part in the Manhattan Project. Condon helped select the Los Alamos site in New Mexico. An interesting coincidence is found in that Los Alamos was close to Edward Condon's birthplace of Alamogordo, New Mexico. Edward Condon helped choose the Los Alamos staff and prepared. And Edward Condon prepared a document on nuclear physics called the Los Alamos Primer that all new scientists at Los Alamos were to read upon arrival. Edward Condon was working as assistant director to one of history's most seminal scientific undertakings, and, according to physicist Edward Teller, Condon was single-handedly responsible for shortening the length of time to the H-bomb by 1 whole year. There is something else worth bringing up. In my researching Edward Condon, I was surprised to learn that he had some tangential possible run-ins with UFOs prior to his taking the Air Force contract in the late 60s, 20 years later. One example of this can be found in his founding of Los Alamos and the role Los Alamos National Laboratory has played in UFO lore, as well as all of the UFO sightings reported around the various other Manhattan Project sites like the Hanford site and Oak Ridge. Another interesting point to note is that the language in the 2023 NDAA seems to indicate that UFOs were spotted and perhaps recovered at the Trinity test site, where the Los Alamos scientists would eventually detonate the first atomic bomb. Now there will be a few more of these interesting brushes with UFOs that Condon would have. Nothing confirmed, but UFO history lovers will find these tidbits interesting, so just keep these in a side box going forward. The brutality of World War II, along with intelligence reports that the Germans were close to developing the atom bomb, motivated the Manhattan Project scientists to put all they had into reaching the bomb first, without much regard for implications and effects an atom bomb would have on the world. Amidst this patriotic and urgent climate under which the Manhattan Project scientists worked, Edward Condon would go against the grain and be one of the first American scientists to raise questions about whether civilian scientists or the military should be responsible for overseeing atomic energy. Condon's problems would be compounded by the secrecy that the military put under the Manhattan Project scientist. Edward Condon clashed with the General Leslie Groves, the Army Corps of Engineer officer overseeing the construction of the Manhattan Project. Condon was angry scientists were not allowed to consult other scientists also working on the project, which made progress difficult. Another point of contention for Edward Condon was that he did not think that the military should be the sole group responsible for this new weapon that was going to be unleashed and the world. Because of these concerns, Condon would resign from the Manhattan Project. In his resignation letter to Oppenheimer and the military officials overseeing the Manhattan Project, Condon would say, quote, "The thing which upsets me the most is the extraordinary close security policy. I do not feel qualified to question the wisdom of this since I am totally unaware of the extent of enemy espionage and sabotage activities. I only want to say that in my case I found that the extreme concern with security was morbidly depressing, especially the discussion about censoring mail and telephone calls." Edward Condon's departure from the Manhattan Project in the midst of World War II was one of the first examples of scientists and the military clashing over who would control and decide how the atom bomb and atomic energy. But more scientists would take this position once the bomb's destructive power was witnessed.